All right, varsity math. Let's take a look at 8, 1, 2. Which way do I slice? Kind of like we sliced pie yesterday. So 812 is the disk method, but it's our fundamental understanding of all volume. So we're kind of just going to walk through it like we did pre-calc. We've had such a strong introduction in this book to graphs of flags. We've been looking at, making this flag and rotating it around the x-axis and talking about what it's going to look like. And in this case, you'd have one cylinder plus a bigger cylinder. You'd add them up with our pi r squared h. Plus, the bigger one might be pi r squared h. Add them up, and we get our volume. You've been able to make that move for the entire year. That was not a stretch when that showed up in our first homework on the first day of school. So we extend that just a little further. Calculus is the mathematics of change, and we began in pre-calculus finding areas under curves. And specifically, they're talking about the curve here is the square root of x. For a long time now, you've been able to say, well, I can integrate, and we did such good pre-calc investigations of what does it mean when we integrate? And we do our left-hand limits and our midpoint limits. And how do we get an even better estimation? Our rectangles get smaller and smaller until their width goes to 0. And then we can add up infinitely many of them. Infinitely many rectangles in pre-calculus, which we were also happy about, gave us the exact area under the curve in calc. So we're going to use this same fundamental along with our fundamental of adding up infinite rectangles, which is what this would do. And we're going to talk about how to find volume now. Very, very similar. So part A says, when we revolve f of x around the x-axis, we obtain the solid as shown. And then we're looking at, and it's obviously better to look at their graph than mine, but we're looking at that typical rectangle. And when I revolve that typical rectangle, when I revolve the whole shape, I think we can picture kind of what this would look like if we did rotate it appropriately around the x-axis. Some kind of a cup, I don't know. And then if I do revolve my typical rectangle, I really like the drawing they have here of the actual width going around. You should be able to see that that's going to create a disk. And a disk forever has had a volume of pi r squared times h. And if I put my rectangle here, and I also rotate it, it has a volume of pi r squared h. So the important question is to ask, what is my radius? My radius in this case, when I revolve around the x-axis, is just going to be my height. What's my height? Oh, that's what y equals. What does y equal? Y equals the square root of x. So when we revolve around the x-axis and we're talking about height, and I'm stressing this because it's going to be important later, we put in what y equals, because that is my height. Makes sense to me. So when we revolve it, pi r squared, and then our dx. dx has always represented the change in x. So we add up all of these x's and all of their changes, because that is our, in this case, our height of each disk is dx, what we're changing by. We could do 1. We could do 1/2. We could do 1/4. We could get smaller and smaller until we get, as dx goes to 0, we would get our exact area, and in this case now our exact volume. So part C asks, use your disks and set up an integral that will accumulate or add up the volume of disks from 0 to 8. So 0 to 8 of pi r squared h. Obviously super convenient to square the square root. We get an x. Pi is just a constant, so we could probably go ahead and simplify that. I don't even know if I need to start a new page. And Mr. Richard always likes to put the pi in front. Got to know that. X dx, the integral of x is x squared over 2. Put the pi in front. From 0 to 8, 64 halves minus 0 halves. 64 halves is 32. 32 pi will be the volume of the solid we made here. Volume is not that daunting. Volume is very important in calculus, but it most of the time comes back to our fundamental pi r squared h. Sometimes we'll have a hole in the middle, but today we are just doing disks, so no holes. I just think there's such good words that we've been using all year that this lesson kind of ties it together. So 13 again reminds us that we have been finding the volume of these flags that we rotate around, and in this case the x-axis. How's that? Decent? All right. I like, again, the diagram they show, showing you one disk in there. So if this rotated solid is sliced similarly to the solid in 12, kind of like we have shown here, describe the shape of each disk. And like its shape is a disk. Like it's a solid quarter or dime or nickel. Like put those up, find the volume of each one, add them up, we can find the volume of the whole thing. That's how you've got to picture disks. No holes. Disks are coins. All right. And then, or I mean, I guess we could call it a cylinder, which is what a quarter, how you'd find the volume of a quarter. And then what is its thickness? Its thickness is always dx or delta x, the change. The smaller the changes, the better our estimate is. We want our change to go to 0. Assume the slice shown in the diagram above, some x value between a and b. What is the volume of it? Well, we said its width is delta x. That's it. Its height or its width times pi r squared, and in this case they're saying f of c. Like just this basic fundamental understanding of c is between a and b, so f of c would be its radius. F of c. If this is c, let's see if I can get another color. If this is c, then its height here is f of c. So its radius is f of c, radius squared, pi r squared, every single time. And then C, here's our basic understanding. The integral from A to B of pi r squared times the height, or the width of each cylinder. There it is. Fundamental understanding. Pi r squared h, all represented right here. All right, draw a sketch in the region of the first quadrant of x squared and a line bounded by x equals 3. So that's got to be 3 comma 9 right there. Imagine rotating this region about the x-axis. So if we go about the x-axis, got to look something like that. Nice cone-shaped, really, if you're looking at it this way. Sketch a solid and show a typical disk. So I think I just did that. Here's your typical rectangle, revolved. There's your typical disk. The volume of that disk is pi r squared h. No holes, nothing to subtract. Set up and evaluate the integral. That will find the volume of this solid. So we went from 0 to 3. To find the area, everyone would know we'd go from 0 to 3 of f of x. F of x represents the height of our rectangle. So now f of x represents the radius of our disk. So the integral from 0 to 3. And again, I, for some reason, was always taught put the pi out here. You'll also see the pi written right here. It's just a number, just a constant. And what is my r? Y equals x squared. So my height is x squared. X squared times dx. There it is. Can we figure it out? Sure. X to the 4th integrated, x to the 5th over 5 from 0 to 3. 3 to the 5th power, 243 over 5 times pi, 0 over 5, of course. So 243 over 5 pi, something cubed. Not bad when we're talking about disks. And it's really, volume is not bad at all. You guys are so good at areas, volume's just one more step. 815 kind of revisits what we were looking at in 13, and maybe I can draw a better picture this time, we'll see. Where from 2 to 5, y equals the square root of 6 minus x. And from 5 to 8, y equals x minus 4. So it says, find the volume represented around the x-axis. So up there we wrote the integral from a to b of pi r squared h. So in this case, we're going to have to probably set up two integrals. The integral from 2 to 5. Now, my typical rectangle is here, revolved. So the height for the first one is 6 minus x squared dx, plus the height for my second one from 5 to 8 is x minus 4 squared dx. Go ahead and plug in your calculator. I think you get 28.5 pi. I like it.